Hello, my name is Miriam Ruf and I'm the research group leader of the group Automotive at Fraunhofer IOSB in Karlsruhe. Today I have the pleasure to talk about the challenges of testing automated and connected vehicles. Traditionally, testing of new vehicle systems has basically been done component-wise on testbeds and testing sites, as well as intensively on public roads with specialized test drivers. But as more and more vehicle functions become connected and automated, the systems become more complex, and also their testing and validation. Eventually, methods of classical verification will not be enough for automated driving. So we need new ways for testing these advanced functions. One first step towards new testing methods is the availability of test areas on public roads, such as, for example, the testing area Autonomous Driving Baden-Württemberg in Karlsruhe. Nevertheless, the validation of these AD systems will not be possible with real driving tests only. Professor Winner from Darmstadt, for example, estimates that 240 million kilometers are needed for validating AD systems, which would be a distance from Karlsruhe to the Sun and back to the Venus. And this high amount of driven kilometers would have to be rerun after each and every small change within the system under test. So this results in a high demand for a combination of real testing and virtual test drives that are validated with real data so that they are proven to resemble the real world. For this talk today, I would like to show you the range of challenges that these complex systems of automated and connected driving are imposing on testing and validation by presenting two examples. But, of course, there are many other important aspects to it, for example, acceptance, market introduction, interoperability, ecology, which I will not be able to talk about today. So let's dive into the first example, which is the challenge of cyber attacks on connected vehicles. Currently, an attack on a vehicle's crucial software stack needs a physical access to the vehicle in order to carry out an attack vector. But the more connected the vehicles get, the more vulnerable against cyber attacks they become. In one project, we have analyzed that a simple mobile phone is capable of interfering with vehicle-to-vehicle messages, so that malware on a wide range of mobile phones could provoke severe accidents. In our scenario, these accidents would not be targeted against one certain person, but rather be effective through having infected a critical mass of mobile phones. So let's talk about this scenario I'm painting. We have our ego vehicle in green, which is fully automated and connected. We have another vehicle in red as a cooperation partner, because it is supposedly also fully automated and connected. And the word supposedly will be very important in just a second. And we have an obstacle that appeared in front of our ego vehicle that we have to avoid. So if we look at the different possibilities the ego vehicle can drive, these different possibilities have different maneuver costs, which range from high costs when driving into the obstacle, over middle cost driving onto the hard shoulder and possibly colliding with one of those road traffic control devices, up to very modest maneuver costs driving into the lane of the oncoming traffic. But only, and this is the important part, in case that the oncoming cooperative partner is driving onto its right lane. In this situation and this constellation, this would be the negotiated cooperative maneuver between green and red. But what if we are facing a cyber attack and the red vehicle in reality is not automated and connected, but rather driven by a human driver? With an infected mobile phone, faking a successful negotiation of this emergency cooperative driving maneuver. The human driver would most likely not be able to evade fast enough, and so this situation would result in an accident. What we did in this project was to develop a countermeasure by using head or taillights to send verification messages, and on the same time keeping the normal function of making light intact. The challenge was to be able to communicate with at least 1000 Hz and at the same time with a cheap system setup, as high-speed cameras are way too expensive for automotive purposes. So the technological realization includes a cheap CMOS camera having the so-called rolling shutter effect, where the different lines of an image don't get extracted at the same time, but rather after another, resulting in a time offset between the first line in the top of an image and the last and bottom line. In order to use the rolling shutter effect, we additionally used an optical low-pass filter to distribute the light signal onto the entire vertical axis. This results in a picture where we see the 1000 Hz flickering in different lines of the image, so that we not only are able to extract a verification code of the negotiated maneuver, but also the position of the sender, which then can be double-checked against another camera with a vehicle detection algorithm. If the headlight's position in the blurred image matches the position we expect the cooperative partner to be, and that we see in a classical camera, the verification message and its corresponding cooperative maneuver is legitimate. So this combination of information is very hard to fake and therefore a working countermeasure against such a cyber attack. Going over to the testing of such system. Questions for the validation of these security aspects are the estimation of the necessity for future use cases of automated and connected driving, and the interaction between cooperative driving function, radio communication, light communication and traffic situation. And the challenges are that especially the interaction between these different areas is best evaluated via simulation, at least at the beginning of development. But in order to model the light communication correctly, you need a very sophisticated physically based optical simulation that at the same time is capable of simulating all the other aspects too. After simulation studies, the prototype testing is another challenge, as you would probably not have the permission to test on public road, so you would have to test the scenarios on test sites. Which then comes back to the simulation again, that, in this case, has a high responsibility to be realistic for the early stages of the development process of such function. The second example I would like to show is the challenge of testing a situation-dependent emergency braking system for an unbounded EE failure. There will be a responsibility shift with increasingly automated functions in the vehicle from the driver to the automated system. So at some point, the vehicle has to be able to cope with severe situations by itself and cannot rely on the human driver anymore. And one of the severe situations might be an unbounded electrical failure a vehicle might have to face. And additionally, this severe situation might arise while the vehicle is crossing oncoming traffic, or passing a railroad crossing, or some similar very delicate situation. The countermeasure we have developed in a project is a situation-dependent emergency maneuver system. That is a combination of the information of the pre-existing situation prediction algorithm, an emergency trajectory calculation. Both of these things have to be lightweight as there is a very limited computational power in a vehicle. And a hydraulic braking system with the possibility to preset the braking moment and braking pressure via a periodically adjustable valve that you see at the right bottom. This valve is preset depending on the current situation and the vehicle's surroundings, and a calculated best emergency trajectory in case a failure might happen in the next instant. But as long as there is no failure, the emergency system has no impact and just keeps on re-evaluating the situation and calculating a best emergency trajectory. Coming back to the testing of such a system. The question of the validation of the safety aspects is the dependence of the system on the artificial intelligence generating the behavior of the vehicle, the EE system, hydraulics, vehicle dynamics, and last but not least, the current situation and the behavior of the other traffic participants in the situation. So again, the challenges for testing are a high correlation of many parameters that are needed in order to validate the system. And therefore, again, there is a high need on naturalistic simulation in order to be able to validate the system in different situations with different parameters and different constellations. But of course, there also need to be possibilities for testing the system on test sites, as tests on public roads are not applicable due to the high risk of such maneuvers. In conclusion, due to the increasing complexity of automated and connected driving, challenges arise in testing those systems. And these challenges are more complex, widespread, and require the testing of the whole system, including the complete surroundings and not only a system part. And these challenges need an interdisciplinary approach. So in conclusion, there is a necessity for all the different testing methods, from virtual testing, over testbeds and X in the loop, up to testing in public traffic. And all these testing methods need to be easily interchangeable depending on the system under test. So this was my talk about the challenges of testing automated and connected vehicles. My name is Miriam Ruf. If you have any questions or suggestions, please feel free to contact me. Have a nice day and goodbye.